This is the seventh experiment of digital design. We start with what are latches and flip-flops, starting with what is an SR latch. SR latch, these are toggle switches and NOT gates, NAND gates that we use to make the phonic circuit. Now, how does the truth table works? You have S standing for set, R standing for reset, Q is the output, and Q bar is the inverse of that. So, if set is 0, reset is 0, then output is 0. If set is 1, R is 0, reset is 0, that means I have set my output to 1, so the output is 1. If set is 0, R is 1, that means whatever is my output, that is reset to 0. And if set is 1, R is 1, then it is an indeterminate state. Now coming to D flip-flops, D latches, the circuit diagram nearly remains the same, just we have D as the input coming over here, this is the inverter, and the rest remains the same. If initially what happens with D latches, whatever you give as the input, the same comes as output. So give 0, get 0, give 1, get 1. This is about latches. Next we come to flip-flops and its application. The next run is about flip-flops. So we will discuss three types of flip-flops: JK, D and T flip-flops, and the run 3 is about the applications in which we will involve how to convert one type of flip-flop into the other. Like converting or making T flip-flop out of JK flip-flop, making D flip-flop out of JK flip-flop, and making T flip-flop out of D flip-flop. So all those will be discussed. Starting with what is a JK flip-flop? JK flip-flop, if you give such inputs, you have these outputs. How do these or what do these stand for? Is if you give 0 in J, K, 0 for J and K, then the output is QT. QT means that whatever was already there as the input, the same thing comes as output. Whatever was stored in the flip-flop. So suppose this was storing 0 initially, so 0 will be coming as output. If this was storing 1 initially, then 1 will be coming as output. Now, when does the output come? The output comes when the clock pulse is given. That is, on negative edge triggering of the clock pulse or positive edge triggering of the clock pulse, that depends on whether this has a number or not. When this happens, when the clock goes from 1 to 0 or 0 to 1, let's say from 1 to 0, as soon as this happens, and with this and this as 0, whatever is there inside goes outside. So that happens for 0, 0. If this is 1, 0, then this does not matter, or the present state would not matter. Whatever is the value of j, the same thing comes out. So for 1, 0, you have 1 as output. For 0, 1, you have 0 as output. And for 1, 1, so that means that you have 2t bar. 2t bar means that if j and k are both 1, and whenever clock pulse is given, if 1 is inside, then the output will be 2t bar, that is 0 will be coming as output, and this will be 1. So that is about JK flip-flop. Next is D flip-flop. D flip-flop, like latches, is straightforward. Whatever you give as input, the same thing comes as output. It does not matter what is the current state or QT. What is the state of or whatever is present inside the flip-flop. You give, you get the same thing. Now, what is the advantage of having something like that is that it will delay, because output will be coming after some period of time, after the next clock pulse. So that's why this will help. This will give the delay, whatever is required in any circuit. It is required at times. Now, what is a T flip-flop? T flip-flop is like an inverter, but it acts according to the states. So, if T or the T state is initially 0, then that means that whenever the clock pulse comes from 1 to 0, or whenever the clock strikes then whatever is given as QT, the same thing will come as output. Now, if it is 1, then whatever is given inside, the opposite of that will come as output, that is QT bar. For T is equal to 1, QT bar will come as output. Now, the next part is run 3, that is the applications of latches and flip-flops. So, as it is visible from the truth table, you can see that these two, and these two, the truth table for JK flip-flop matches with T and D as well. Just a little variation is required. So I can say that when J and K are both same, then I get something like a T flip-flop. So in order to make a T flip-flop from a JK flip-flop, just take it and short both J and K. You get a T flip-flop. Next is how to make a D flip-flop from a JK flip-flop. As it is evident that these have similar truth tables, so what can be done is, given a JK flip-flop, a NOT gate can be connected to this side such that when D input is given, suppose I give 1 over here, then 1 goes to J, J is 1, K becomes 0, so K is 0 and I should get 1. So I gave 1 here, I got 1. Gave 1, got 1. Gave 1, got 1. So, sorry, gave 1, got 1. Now I gave D is equal to 0. If I gave 0, J is 0, K is 1. J is 0, K is 1, output is 0. Gave 0, got 0. Gave 0, got 0. So D flip flop is implemented. Now I have to make a T flip flop out of a D flip flop, which is over here. Yeah, this is a D flip flop. So the idea behind using a D and T is kind of toggle. So taking the Q output, that is the output that was there after the purpose was applied, this output is given as or fed into the flip flop directly using an XOR gate. What will the XOR gate do? If T is equal to 0, then if T is equal to 0, I will get Q directly. That is, an XOR gate works as if this is 0, whatever is given, the same thing comes out. If this is 1, whatever is given, the opposite of that comes out. So, whatever is given, if this is 0, then whatever is given, that is Q, the same thing will come out, that is QT again. If this is 1, that is T is equal to 1, then whatever is given, that is Q, then QT bar will come out. So that's how we generate T flip flop from a T flip flop. That's about all the experiments of, that's about experiment number 7.